So one of the more interesting aspects of a discussion of electrochemistry is that it allows you to understand electroplating. And you've probably have heard of this before. What electroplating allows you to do is put a layer of a metal on top of something. And so the most common one is putting chrome onto, say, a muffler or something like that. It allows you to plate or put a small layer of a metal on top of something else. And in this discussion with chemistry, we're going to be able to understand really what's going on in that electroplating process. So the idea is we're going to be taking a reduction half reaction. So here we are taking Ag plus and going to Ag solid, and you can see, and we talked about this with the cell reactions, that if I put electrons into solution with Ag plus, what it's going to do is produce silver solid, and that silver solid is going to form on whatever we make the cathode. So overall, we're going to be taking a half reaction. We're going to be putting a cathode into solution with whatever metal we're interested in. In this case, Ag plus. We're going to pump electrons into that cathode. The electrons are going to interact with the Ag plus in solution, and that's going to cause Ag solid to form on whatever we want to be the cathode. But the idea is, if we understand the flow of the electrons and we understand the stoichiometry of this reaction, we can actually calculate how much of the metal is deposited. And so this is an important idea when people do electroplating. So the first thing we need to do is know how many electrons we're actually pumping into the reaction. And with us, the idea that we use is current, which is amperes. You've probably heard of them as being amps. That's something that is used to describe the flow of electrons. And so we're going to go with that. But current, or amps, are just a charge per unit time. And what we use for charge is a unit called a coulomb. And a coulomb is related to the charge on an electron. So amps, or current, is equal to coulombs per second. And coulombs are related to the charge of an electron. And how they are related is by F, or Faraday's constant. And really this says that 96485 coulombs per mole is relating to the charge. It's literally the charge on 1 mole of electrons. So if we know how many coulombs we're putting into something, we can figure out how many moles of electrons we're putting into something. And that's really how this starts. So here's a classic question. I'm doing electroplating. I hook something up and I put it into a solution of silver plus. I apply a current of 1.5 amps for 15 minutes, and I want to know how much silver metal is going to be deposited. So I've given you enough information. Really, the first thing I need to know is what's the half reaction that's going on. So remember here, the stoichiometry between my metal and electrons are 1 to 1, but they're not always like that. Like if I was using copper 2 plus, it would be 2 electrons for every copper plus. And so this stoichiometry is going to come into play a little bit later. So I really want to consider what my half reaction is. So this half reaction tells me that for every 1 mole of electrons that are added, it causes 1 mole of Ag plus to turn into 1 mole of Ag solid. So here, if I know the current, if I know how many electrons I'm putting into the reaction, I can tell how much silver solid I am getting out. So the first thing I need to know is the number of coulombs. And in coulombs, the unit is going to be in seconds. So we typically do electroplatings over long periods of time. So the first thing you need to do is find out how many seconds. I told you 15 minutes, 60 seconds per minute. So I've allowed this reaction to go on for 900 seconds. I then use the fact that current is equal to charge divided by time. Current's in amps, charge is in coulombs. So if I'm looking for charge, time in seconds times the number of amps tells me the charge in coulombs. So I told you I was applying 1.50 amps. I let it go for 900 seconds. That means I have 1.35 times 10 to the third coulombs. That's how many, related to how many electrons I've put into this reaction. So now I don't want coulombs, I want moles of electrons. So really remember, even though involves an electron, this is still a reaction. It still involves stoichiometry. And I want moles of things. It says for every 1 mole of Ag plus, I use up 1 mole of electrons to make 1 mole of Ag solid. So I don't want coulombs. What I want is moles of electrons. And that's where Faraday's constant comes in. Faraday's constant tells me the charge on 1 mole of electrons. So my Faraday's constant, F, is equal to the charge in coulombs divided by mole of electrons. Or if I take the number of coulombs divided by Faraday's constant, it tells me how many moles of electrons I've put into a situation. So I just calculated that I put in 1.35 times 10 to the third coulombs of charge into my reaction. I divide by Faraday's constant. That tells me that I have put in 1.40 times 10 to the minus second moles of electrons into my situation. Then I got to remember, I don't want moles of electrons. I want moles of my metal. So I need to use my reaction to do a stoichiometric conversion. So just like what we did when we were talking about limiting reactant problems, I know how many moles of electrons I'm putting in, but I want moles of Ag+. This reaction says that for every 1 mole of electrons I'm putting in, I get 1 mole of silver out. So it is a 1-to-1 ratio. So the moles of electrons will cancel, and I'll be left with moles of silver in this case. So because it's 1-to-1, it's equal to each other. So I know I'm depositing 1.40 times 10 to the minus second moles of silver. But you got to remember, sometimes the stoichiometry might not be 1-to-1. So if I had copper 2 plus 2 electrons going to copper, this number would be a 2. So it's very important to consider the half reaction and the stoichiometry involved in there, because this may not be a 1-to-1 mole ratio. So now I know how many moles of silver that's being deposited. From here it's pretty downhill. I want to know grams. Moles times molecular weight gives me grams. So I know how many moles of silver I have deposited. I go to the periodic table. I get the atomic weight of silver, so 107.9 grams per mole. I multiply together, and I figure out that during my 15 minutes I've deposited 1.51 grams of silver.